Good afternoon, everyone. Indeed, I would like to talk about similitudes of quadratic forms. Let me introduce them with the following little example, maybe. Let's have a look over the field 2 of rational numbers at the following quadratic forms. So by which I mean homogeneous polynomials of degree 2. So let's look at x squared plus y squared. And we also rescale this form with the number 3 and the number 4, let's say. And one can wonder whether rescaling the form actually changed this essentially or not. Now, for example, we could note here in the bottom example, we can rewrite this as 2x squared plus 2y squared, meaning it's essentially the same form as the first one we had, up to a linear transformation of variables, right? And so these two are essentially the same in this regard. But however, if we rescale by 3, then we see that, for example, this form represents 3. We plug in x equal to 1, y equal to 0, we get 3. However, we know we cannot write 3 as a sum of 2 squares in cube. And so meaning these two are kind of essentially different. And this will be the idea of similitudes, a factor which, after rescaling, does not affect by too much the quadratic form. So let me now give the definition of it in generality. So let's say we have a field K throughout this talk always assumes to have characteristic not equal to 2. So the quadratic form goes nicely. Then let me give the definition. For phi a quadratic form over K, we set G of phi to be all non-zero elements in our field K, for which rescaling the form phi gives the same form phi again, whereby this, I want to introduce this formally. This is similarity, rather isometry of quadratic forms. So you can think of this as the same up to, as before, a linear transformation of variables. And two things to note. And so first of all, this is what I call the similitudes of phi, the elements here in G of phi. And two things to note. Then on the one hand, it's a group. And moreover, it will be a subgroup, of course, of K star. But moreover, it will contain all the non-zero squares. Which will be known as such. Indeed, by this reasoning here, that we can rescale by squares and still not affect the quadratic form. So it's a group containing the non-zero squares. Now, before we move on to the second big important thing of this talk, I will first state a result, which talks a bit about how these groups G are kind of well behaved along field extensions. And it is the norm principle due to Shalal in 1969, saying that if we have a quadratic form for phi, a quadratic form over K, and L over K a finite field extension, then in fact we have that if we apply the norm of this field extension to the similitudes of phi lifted to L, so as a polynomial, you can say we regard this now as a polynomial over L rather than K, and the similitudes of this form, applying the norm to them, actually lands back into G of phi. So this way they're well behaved for field extensions, at least finite field extensions. And so this will allow us to now make the second, introduce the second main player of this talk. Are you ready? Yes.
And do you know some examples for this quotient by the square is finite, or by some field or some quadratic forms that like?
So you mean where this quotients. We know examples where square classes are finitely many.
Okay.
For example, the p-adic numbers, for example. But we have to think first examples where there's infinitely many square classes, but this one's finite. So we have to think.
Exactly. I was thinking in the infinite class and then this.
Yeah, that would be if you think about it. But especially any field having finitely many square classes will have also finite index in this regard. And so for a quadratic form phi over k, we make two definitions. First of all, we set phi plus phi to be, we take first the sets so what we do is we take m over k finite extensions where phi becomes hyperbolic. I forgot to write what I said. And also this I won't introduce formally, but you could think of it as kind of the equivalent of a polynomial splitting, so having as many roots as possible. Also here, the form will have as many roots as possible over this, this field. So what do? We take any finite extension making this phi hyperbolic. We take any norm back to k of such a similitudes of the form, and we take the group generated by this. And I can also say this will turn out in fact to be precisely the non-zero elements of m, precisely by phi m being hyperbolic. But now this we now use to make the second definition. Because this is the definition as is this one. And we now say, let's define h of phi to be the product of these two groups here. And so what do we see? We say that by definition now of this h, the non-zero squares are a subgroup of h of phi. And on the other hand, the squares are all contained in g of phi by what I said here. On the other hand, if we take the norm over a finite extension of some similitudes, we end up having a similitude again, meaning that these two, hence h of phi itself, will lie in our group G of phi. Okay, which, if you want to finish the chain, once again lies in the non-zero elements of K. And so this chain of the inclusions of subgroups. And now the billion-dollar question for today. Will be to ask or to investigate whether h of phi is in fact equal to g of phi or not. So whether h is a strict subgroup of g or actually equal to it. And I can provide some motivation for the more geometrically inclined. And so why would one care about such a question? Well, one can note that if one has that for any field extension L over K, these two are equal. If this is true, this is precisely the same as a certain linear algebraic group, namely P sim plus. So linear algebraic group one can construct from this form phi. This is equivalent to it being our trivial. And so the geometric notion comes up here, because we have that for a variety to be stably rational implies that it is our trivial. And so if we could find a form phi and some extension where h is not equal to g, then we will have found an example of a non-stably rational linear algebraic group by these two facts. This could provide some motivation as to why bother doing this. Let me say the first fact. which is not hard to show.
Can you say a second? What is this PC? Is a subgroup of O?
Honestly, I wouldn't know myself too much about this.
But
But this is some linear algebraic group one can construct from phi itself.
So it's in
can I fill in?
Yes.
Yeah. So in fact, it's closely related to this G, but actually we also call these elements of that G rather normally called rather the factors of similitude.
Yeah.
And the elements of this P sim are the similitudes. What is a similitude? It's basically the map giving the isomorphism from phi to C times phi. So one similitude is basically a transformation from phi to some C of phi, and the corresponding factor of similitude is the C. So you should think of a linear transformation of the vector space, which transforms the form up to a scalar. That is this group without the plus, and then the plus is somehow the connected component in this as an algebraic group, which is an F index 2. If that's and that's an interesting algebraic group, and with that we can.
So it contains both.
It contains
in between GL and O,
and the P sim plus contains the SO. So it's a kind of and the interest of the question comes from the fact also that O is a rational, SO is a rational group, but this slight enhancement of the orthogonal group or the special orthogonal group is not necessary. Well, not it's more complicated.
Yeah.
This can provide some motivation, but so I won't talk more about this angle in the rest of the talk. And so to now wonder about when this equality holds, I've already stated the following fact. Say we have a quadratic form phi over k of dimension at most phi, and where by dimension I kind of mean the number of relevant variables. So by relevance, a silly example would be if I give you the correct form in x, y, z given by x squared. It has three variables, but kind of essentially only one, right? So it's kind of to avoid such pathologies. So if the dimension is at most 5, then in fact h of phi will turn out to be equal to g of phi, but not complicated arguments, but basic arguments. And so one can note also here, so one already gets the equality, but even more so one can note that dimension is something which stays the same along field extensions. And so if a form is of dimension at most 5 over k, it will remain so over any field extension. And so we now get this field independently, this equality. And so up to 5, there's nothing interesting happening. And so let's now talk about what happens in dimension 6, which will be more interesting as the title suggests.
Maybe one question.
Yes.
Like in odd dimension.
Yes, it will turn out.
What does hyperbolic mean there? I mean.
Actually, yes, that's a good point. It will turn out that's for odd dimensional forms. Anyway, this will turn out to be true. And so one can, in fact, from the start, only talk about even dimensional forms.
Okay. So the answer is easy, but the question is actually not clear.
I mean, hyperbolic,
because hyperbolic does not
imply.
Yeah, I mean, yes, true. So one could, at the start, before, in this sense, I know you're right. Yes. In this sense, I have to amend it.
I mean, if you take this H anyway, it contains the squares, and then you could say even if this is kind of the trivial group,
yeah,
square.
Because in any case, for an odd dimensional form, they will both turn out to be the non-zero squares. But then yes, one can then define the item to be the one group, for example. But so yes, the question is kind of only interesting for even dimensional forms. Good. So saying what about six dimensional forms? Okay. Okay, so as I've mentioned, the story will be more nuanced in dimension 6. So we will sift our quadratic forms through invariants. And so let me first mention the first invariant one we'll discuss. Let's say with the quadratic form phi given as such. Where in fact one can note, as long as the characteristic of the field is not equal to 2, one can always find a linear transformation of variables, making it so that the quadratic form is given by these pure parts only, no mixed parts. So this is in fact, even though it doesn't look like it's a general way to write a quadratic form. So to a quadratic form, we associate its discriminants, which will look like this. It will be plus or minus 1, sorry, minus 1 up to this thing times and so we multiply all with the coefficients ai, and we multiply by minus 1 or 1 depending on dimension of phi. And this will then be an element in this in a square class group. And so this way we can assign to any phi such an element in x squared or in x star, k star mods with squares. And now we can say the following. Again, something which is not too deep to prove. If we have a quadratic form phi having dimension 6, and either the discriminant of phi is trivial, meaning it's just the class of the squares, or the discriminant of phi is non-trivial, so represented by some d, which is a non-square, and we have that phi has a non-trivial root over the field where you join the square roots of this d. So in either of these cases, then also we get still that h of phi will be equal to g of phi. And so again, we have now with this more, we have sifted some quadratic forms which still have this property of h being equal to g. And again, we can notice it also behaves well along field extensions. Because for example, if something is a square in k, it will remain a square in any field extension. And also, if we have that it becomes a form over its discriminant fields, it becomes, or it has a non-trivial root, then it will also be the case over any field extension, because if we have field extension m over k, either d will be a square, and if it is, then we're in the first case again. If it isn't, then we can make a diamond where one can add the square root of d to the field. And now since our phi already has a non-trivial root here, it will also have one here. And so both behave well along field extensions. And so again, we have nice results saying that these two are in fact equal to each other. And this will now bring us to the bad boys of our story. But for this, let me make one last introduction of a different invariant still. Namely the even Clifford algebra. Okay, this, just words on this. If we have our form phi, let me use a notation where T of Kn is the tensor algebra of the K vector space K to the power n. And so by which I mean this. Now one can define Clifford algebra of the quadratic form phi over k in the following way. Clifford algebra is given by this tensor algebra quotiented by the relation where for any element v in our vector space KVN, we replace v times v with a tensor by its evaluation into the form phi. In this sense, this will provide an algebra that we can associate to phi, and by this relationship, we see that this algebra will have a z mod 2z gradient. Meaning we can decompose our algebra into an odd part and an even part, and this is then where the even Clifford algebra comes in. So this is what I would call the even Clifford algebra. Fine. Okay, so now we have the second invariant that we can assign to a quadratic form. And so now we come to the bad boys of the story. Because now we have been looking at six-dimensional forms having either trivial discriminants or non-trivial discriminants, but the form having a non-trivial roots over the bigger fields, over the field where you join square root of d. So what about those where they actually don't have the non-trivial roots over these fields? So let me say the following thing. For if we have a quadratic form phi over k, the following are equivalents. So we can either say that the equivalence, as I was saying before, is non-trivial, so given by some b, a non-square, and phi has no non-trivial roots over this field where we add the square root of b. This turns out to be equivalent, again, null factor true, to this even Clifford algebra phi, C naught phi, being a division algebra. That is to say, has no non-zero zero divisors. Yes.
For one of the two implications, you want the dimension to be.
Sorry, yes, I do, yes.
Maybe you can say for which one.
I mean, I want to have it at the beginning. Yeah, because this is indeed important. We're talking about three-dimensional forms. Yes, so we stay in the realm of six-dimensional forms, and so we can kind of more neatly package the information of the missing link still. This link of having non-trivial discriminants and not having any non-trivial roots over the discriminant fields. We can package it by saying, well, it's the same thing as asking the even Clifford algebra to be a division algebra.
So in general, this would one implication would still hold, so the lower thing would apply the upper one, but not in general.
Yes.
Not
Actually, the statement is still that these two are equivalent. Because now it seems that.
Ah, yes, certainly. Yes. Yes, so in dimension 6, these two are equivalent. Yes, exactly. Good. So this allows me now to state the result by Merkurjev from 96. Good. So if we have a quadratic form phi of dimension 6 over the field K, then it is equivalent to say that the even Clifford algebra has no non-zero derivative on this. This is equivalent to, as it turns out by Merkurjev, the existence of some field extension f over k, such that h of phi over f turns out to be not equal to g of phi over f. And so if we backtrack, we already have one implication. We have the implication, let me say it right. We have the implication top to bottom. Because now if we, by previous cases, right? Because if we have a correct form of dimension 6, three things can occur, either one of these two or the last fact here. And so it remains to show now that if, I forgot to, okay. And so the last thing to show now is if we're in this case, let's just say if one of these two equivalent things is right, then in fact there exists a field extension making that h is not equal to g. Will we still say, because I will use it later?
Possibly infinite dimension.
Yes, yes, it will be. Yes, I can already state this now. This is part of what I will talk about in a second. So in the method that Merkurjev proves, by making some clever choices, one can make sure that this extension is of transcendence degree 8.
And I want to add some, what you said before as motivation, just for your information, also comes from that same paper of Merkurjev.
Yes.
So, this was basically the way how to get the first examples of non-trivial cases for this p-sim plus.
Yes, this result was part of a bigger Merkurjev into whether linear algebraic groups are trivial or not. Yes. And so notice how this is, on one level, quite satisfying in the sense that now we have characterized precisely when, for dimension 6 forms, we can find a field where h will not be equal to g. This is on one level satisfying. On the other hand, suppose we have given a field, specific fields, and a single-dimensional form. It would be nice to know if actually over the field itself already we have not inequality or equality. And so in this light, I cannot talk about something which I did, is to bring down this transcendence degree to 2. And so by going about it in a bit of a different way, one can prove that one can already find such a field extension of transcendence degree only 2. So for this, let me introduce a notation which I forgot to mention here. So let me say such a form satisfying these equivalent definitions, equivalent properties. We will call for this talk a Merkurjev form. So that's to say, a 6-dimensional form for which the even Clifford algebra is a division algebra. Those things are Merkurjev forms. And so the statement is then, in the Merkurjev form, well, those are precisely 6-dimensional forms for which we can find an extension making h not equal to g. And so what I want to talk about now is that in fact, if we have a Merkurjev form mu, Merkurjev form over the field K, then in fact, there is just a field extension P over K of transcendence degree 2, having the property that's already there, the h of mu is not equal to g of mu. And so for this, let's have a look at a sketch of proof of why one can already find one of stresses degree 2. Let me first need some space.
It's your result.
Yes.
Really feel.
Yes. It should not be equal to 2. Okay, so let me give a bit of a sketch of the proof in a few steps. Okay, the first step is that one can in fact write our form mu in the following way. Okay, so by some basic manipulations, one can rewrite mu in such a fashion where all the AI, BI, and D lie in K, with D representing the class of discriminants of mu. And this is now useful because by the next step, it will turn out that in fact these parts, not this one, are the ones which actually matter. This is for the following reason. On the one hand, it is true that if we the group G of similarity factors of 5 is itself invariant under rescaling of 5. As we can see, because in the definition which is now gone, we can cancel any factor of similitudes by a linear change of variables. And so in this sense, it won't matter up to rescaling what this G is. And then on the other hand, we have the following fact also, is that if one can write 5 using up to isometry as if one can break up the form phi into 2 distinct parts, with different variables, and there's no overlapping variables in the 2 parts, then the intersection of g of phi 1 with g of phi 2 will in fact lie in phi. This is quick to see, because if we now say, for example, we look at c times phi, if I write in short, this is then c times phi 1 plus c times phi 2. And so if c is a similarity factor of both phi1 and phi2, we do not change either of those two, meaning we haven't changed phi itself. Right? And so by this reason, if we find an element which lies in G of this part, and of this part, by these two facts, then we have found something in G of mu. Okay. So far, so good. Now the third step is then to, in fact, start making an element which will end up lying in G of mu. And for this, we look at the irreducible polynomial P. The irreducible polynomial of this element, which I will call beta, over K. And so my claim is for this element P, it will in fact turn out that P lies in the similarity factors of the first two ones. And this over the field where we join out T as a variable. So this is my claim. So meaning if we can now, once we know this is true, if we now can also obtain P over some bigger fields, as we will find out, where it also becomes a similarity factor of this one, then by this step 2, we find something in G of mu. Okay. Over K.
So can you say something about this? I mean, this irreducible polynomial, what degree does it have?
We'll have degree 4. So yes.
So, yeah, maybe say something about this field.
Yes, this is going to draw this in just a bit. And so what we do, or we have, is that if we adjoin beta to K, it will be the same as the quadratic extension given by n squared of A1 and squared of A2. So it is degree 4 extension over K.
Yeah, but I mean, the fact that this is actually biquadratic, so it's basically requesting that the A1 and A2 are non-squares and are
yes,
and so on. And why?
I mean, this I wasn't going to go into, but indeed, I would say to just have it be part of the sketch proof. So indeed, we will. I mean, for one, for example, they can be squares, either of them, because if one of the two were a square, say for example A1 is a square, then this one will have a root over K, but we requested mu to be in a Merkurjev form, which means it doesn't have a square roots, a non-trivial roots, even over the field K drawn squared with D. Yeah, so indeed, so these ones definitely cannot be squares.
Just want
okay.
to encourage to link this to the property of Merkurjev form.
Yes, exactly.
That you are assuming that this will actually be a degree 4 extension and that this will be the root.
Yes, that's right. Good. So, can we still say? Let me maybe adapt this round over. So let me say it's rather already with a fairly t added to it. And we have this extension now over kt. And what I want to say is, so we notice how p, or rather, okay, what do I want to say? Yes, so we have over this field, since we have a joint square root of A1 and square root of A2, as I was saying before, these two forms will become will have a non-trivial roots over k beta t. by virtue of A1 and A2 now being squares in this bigger field. And what would you say so? So we're going to have a G lines in here. Yes. One can show that if we look at this extension here, and we take the norm of t minus beta, we will precisely end up with p. And so this is by some small effects involving the embeddings and the gamma theory of the fields. By realizing this norm as the product of the different conjugations of t, of t minus beta. But so once we have this fact, then p is a norm from this field here. Now in this field, both this part and this part become have non-trivial roots, and they're even hyperbolic. And then this is by something which I said in the beginning. Since p, wait, let me write it down. Two really different names. This is part P1, part 1, and part 2. Okay. So as I was saying, P is the norm of some elements lying in a field where both 1 and 2, these two forms, become hyperbolic, meaning by the definition of hype that they lie in hype. And now, as we know, hype lies in the G of this thing. And this proves a claim that we have. Okay, this is going to be here of step 3. And now step 4 is, on the one hand, the most technical one, but also the neatest one in some sense. That is step 4. What we do is we will now force P, which is already lying here, to also become a factor similitudes of this part of the form, meaning it will then be lying in G of mu. But at the same time, we will avoid it from becoming an element of H of mu. This we will do by using the following field extension. P so if we construct this a priori domain of which we take the fraction fields, we now force there to exist elements small x and small y, having that P can in fact be written in such a fashion. And so this will make that we have this following diamond of fields. Where now one can see these will both be the function field of the comic over the base fields, where this one the function field of a non-split conic, as it will turn out, and this one is a split conic. As this will now, by the definition of this conic and its function fields, and how it becomes split once we add square root of d, by some valuation theory arguments, it will make that in fact
P will now lie
in G of our remaining part as well. Multiplying the H of mu. And so as I said, this remaining thing with the previous things we had, implied by step 2, that P lies in G of mu. Okay, this is definitely something worth looking at, how this neat construction of the conic makes this dual purpose come true. Okay, good. So far, the sketch has proved of this fact. So now we have indeed constructed this E as first adjoining a variable to K, so 1 degree of coincidence, and now taking function of a conic, which is the second degree of coincidence. So we need to end up with 2.
So this left one, that it is a function field of a non-split conic.
Yeah, this requires some work.
Is super crucial.
Yes,
Not
I agree.
split, and
And also that splits is also crucial. Yeah, both. You know.
and
Good. And so now we have a slightly improved version of this theorem by Merkurjev, providing the existence of some place where each h is not equal to g, provided that the C naught of phi is a division algebra. And then we end today by giving a way to construct in fact over a specific type of fields such things. Because I still wonder how does one achieve to find Merkurjev forms, which I will end now today with. Good. As promised, let's construct a Merkurjev form. We'll do this over a type of fields which is dear to my heart. We will do this over function fields of p-adic curves. So let's P be an odd family. Being odd is important for the story. Let P naught be a finite field extension of the field QP. And let E be the function fields of a curve over E naught. And so transcendence degree 1 field fields over extension over QP. You can even leave it into results. So what can we say then? Okay, and so then, as I claimed, we can construct an equated form over E. And so also here, let me give a sketch of how we can do this. Good. First of all, what we want is to take a valuation, a discrete valuation on our field E. It's called V, having that its residue fields is the function fields of a curve over finite fields. And we can do by, for example, if we take the complete valuation on E naught, we can lift it to E, or rather to the rational function fields with the Gauss extension, and then lift it to E. Just for example, this would be a way that one can definitely know for sure that one can't find the discrete valuation satisfying this. So now the important thing is that we now have as residue fields the global fields. This will now be something we can exploit. Because now, let me call the residue field K. Secondly, we take a biquadratic extension K. So again, this type of extension comes in. Which we realize as the adding of square root of C and D for certain elements C and D over K. And we can note that K has infinitely many square classes, so in square classes, so we can indeed find a biquadratic extension of K. And now there's some deep result that we will use, which is a Chebyshev density theorem. And so which is true of a number of fields as it is true over global function fields. This machinery will make sure that we can in fact find some elements A and B in K such that the following quadratic form has no trivial roots over this big field K, square root D square root C. This is to do with controlling which primes completely splits over a certain finite extension of the global fields. This will enable us to find a Quaternion algebra or similar or equivalently such a form, which in fact has no non-trivial solutions over these fields. And this now paves the way towards defining something which will lead us to this mu, which we're looking for. Good. So over the field K, given these ABCD that we have now come across in our constructions, we use those to define these two quadratic forms, and they will both have non-integral roots over K. Step 4 is. And then in step 5, what we do is, if we can have effects, so we have K being the residue fields of our valuation K. And so we can find some lifts of these elements A, B, C, D to the field E itself. Good. And so now we have a discrete valuation, so we can take an element, or let's say we can take up to potentially rescaling an element of value 1. Then this allows us to do the construction of mu, namely as and so we use these two components. These two components that we defined here come up in the construction of our mu. And so as that plane, this will be the one to predict time. Let me maybe just hint at why this is true, again, visually through the diagram of field extensions. We have field P and residue field K. We have a biquadratic extension here, of which a sub-extension is the one where we only add square root of D to K. And now it will turn out that D tilde, this lift, will not be a square in B, meaning we can construct the extension E adjoint square root of D tilde. And it will turn out that the residue fields, so we have a valuation V that we chose in the beginning in step 1, which we can lift to some valuation W over the bigger fields. And its residue fields will precisely be isomorphic to K squared root D. And so if you remember the characterization of a Merkurjev form, it has to be of non-trivial discriminants, and so which I claim is indeed this D tilde items, I should say. And so discriminant is obtained by multiplying all the coefficients, as I introduced at some point, and then adding -1 because mu is of or rather multiplying by -1 because mu is of dimension 6. And so indeed, discriminant of mu, if we see A tilde appears twice, B tilde appears twice, C tilde appears twice, pi also, and only D tilde appears once. And so in this multiplication up to squares, we indeed see that the discriminant will be the class of D tilde over E. So for V is a null square. So as I was saying, by this characterization we saw of Merkurjev forms, we can show that discriminant is non-trivial and mu remains or still has no non-trivial roots over the field where we enjoin the square root of its discriminants. And indeed, as we will see, or as we can see, the lift of mu to this field can be built up as the lift of these two forms lifted to this one. And so since we know that this first part has no non-trivial roots over this big field, which is because C tilde becomes a square, and we know that this one has no non-trivial roots. So this is why we know that the first part has no non-trivial roots over this field, and so also over this field. And likewise, C tilde is not a square, even though D tilde is, or rather, D becomes a square in this field, but C doesn't. Meaning that this part also remains, or still has no non-trivial roots over this field, and this will make sure that then the lifts also will be will have no non-trivial roots. And so by looking at this diagram and then doing some more work, we can see that mu has no non-trivial roots. Over this field. Meaning mu is a Merkurjev form over E, and meaning that we are done with the proof. All right, this is what I wanted to talk about today. Thank you.